Hello, everyone. Thanks for joining today. My name is Andonis Aristilu. I also go by Tony. I am a senior technical consultant at Wolfram Research Europe. And today we'll be covering a bit about the Wolfram React-Boilerplate, which is it started as a personal project of mine. And the idea of this is to kind of allow cross-platform applications to be deployed in an easier way. So if I want to deploy an application on web and desktop with a shared front end, I can do that pretty easily with this boilerplate. So before I get into the actual content, I want to just do a little bit of preamble about some stuff that I'll be covering. So framework is something that I'll be mentioning a lot. So I just want to give a little kind of, I just want to define what I mean by that. So when I talk about a framework in the context of JavaScript, in this case, we're talking about a set of like pre-built, reusable set of libraries, tools, conventions, and so on that extend the core functionality of the language in some way. They could do this by making code easier to write, by introducing new abstractions that kind of make code more robust or easier to read, or whatever else. And there's also larger frameworks that will introduce just completely new ways of packaging your code as well. So one of those is Electron, which we'll talk a little bit about. But the idea is for most frameworks in JavaScript, you'll write JavaScript, and if it's a front-end framework, it'll use that JavaScript to generate some static HTML, CSS, and some JavaScript as well. So our front-end frameworks are React and TypeScript. So React is originally designed by Facebook, and the whole idea of it is to make reactive web page design easier to do, right? So it focuses on reusable component-based rendering. So you write all your React parts in these React components, which you can reuse throughout your application. And it also, because it is basically a set of JavaScript functions which generate static HTML, it also introduces a new kind of file format called JSX that allow you to write those React functions in a more kind of markup style that you might be used to when it comes to defining a front end. TypeScript is another one that we'll be making use of, and TypeScript just adds a type system to JavaScript. So it attempts to make JavaScript a strongly typed language, and also kind of integrates heavily with the VS Code and giving you a really nice development experience. It also interoperates with React, so we can use TSX extensions instead of JSX to define TypeScript React files. And finally, the big kind of desktop packaging framework that we'll be using is something called Electron. In Electron, it's slightly different in that it doesn't actually kind of introduce new syntax, or it doesn't actually generate our HTML, our static files. But what it does is it takes our static files and packages them in a way where we can run them as a standalone application on the desktop. And how it does this is it bundles a Chromium install and a Node.js install with all your dependencies into binaries, and that gets sent to the user as a kind of standalone installer that gets installed on their machine. And when they open the application, it essentially just opens the Chromium browser, rendering those exact static files, right? Before we talk a little bit more about Electron, I just want to mention it is a development convenience framework. So it has in mind developer convenience more so than pure efficiency. And why I say this is because if you notice from everything I've described, this will mean that every single application that I bundle with Electron will have its own instance of Chromium and its own instance of Node.js. And that means that the minimum bundle size is about 50 megabytes. So if I'm doing anything with a really small application, this overhead can be kind of a deal breaker, right? But for any bigger application, when that 50 megabyte doesn't matter, the convenience of being able to share a front-end source between my web application and a desktop application, it kind of outweighs that. But I just wanted to mention that quickly. But a little bit more about Electron and how it works. So let me scroll down. So Electron is separated into two distinct processes. So when I run an Electron app, there are two distinct processes that handle that. The first one is the main process, and that is a Node.js process that is acting like a backend, and that is what is actually responsible for managing the lifecycle of the application. So it starts the window, it kind of preloads all the stuff for the Chromium browser, and it also is able to interface with the local machine at a low level and acts as node modules like file system or crypto. So if I need to do any of those things, if I need to interface with the machine at a low level, I have to go through the main process, because the renderer process, on the other hand, is just the process of that Chromium browser. It's essentially just the browser, right? So it renders our front end, but it cannot directly interface with the local machine. It can't use node modules. It can't use FS or crypto. So if I want to do that, I have to go through the backend. I have to go through main. And for these two processes to communicate, we have to set up an IPC mechanism. So IPC standing for inter-process communication. And in this case, Electron has a kind of built-in IPC mechanism called Electron IPC. And what that essentially boils down to is two event emitters that can be used to set up event-based messaging between the processes. And what I mean by event-based is that the process can send messages on a specific channel, or they can listen for messages on specific predefined channels. So again, practically, this looks like just a couple of event emitters, IPC main for the main process, IPC renderer for the renderer process, and they will both have methods like send, on, and once for sending messages, setting up event listeners, and so on. But we'll do more on those in a bit. Right, so with all that kind of preamble out of the way, I want to give a little kind of intro into what the Wolfram React boilerplate is, and kind of a small intro as to how it does what it does. So just starting with the motivation, the main idea of WRB is that at RAL Consulting, a lot of clients would have the need to develop standalone applications, whether that was web or desktop. And our approach actually differed between the two. So web applications were built with a React frontend paired with the Wolfram language backend, all of which was hosted either on a Wolfram cloud or an application server. Whereas desktop applications were often a pure Wolfram language approach of just read books that we send directly to the clients. So yeah, the idea of unifying both of these approaches, so if we have an app that needs to be deployed both on web and desktop, they have a shared front end, and that just significantly makes maintenance easier. Right. So here's an intro into WRB. So this is what the whole idea of WRB is to allow this. So it does this by separating the main package into different npm sub packages, right? So instead of having a single kind of big package, we've got a bunch of sub packages that do different things. So the front end package just defines our front end as a standalone React component that we can import. The Wolfram language package that just defines all our Wolfram language scripts and expressions. Our desktop package will actually handle the bundling and building of our desktop application by importing that front-end component. And same with the web. The web will do the same for our web files. And again, it will import that from the same front-end component. All of this stuff is managed by something called Yarn workspaces. Yarn is another kind of package manager for Node. It's used to manage your dependencies and also manage your workspace. And Yarn workspaces is specifically for monorepositories with multiple npm packages. So I'm able to manage this as a single kind of package, even though it's made up of multiple sub packages. All our web static files are built using something called Vite. So Vite, it provides a development server for when you're developing, and it also it uses something called rollup to build your static files, so your HTML, JavaScript, and all that. So it compiles your React and TypeScript into just static HTML. And finally, our desktop apps are built with the Electron version of Vite. So Vite has also Electron Vite, and that does a similar thing. So it will set up development servers, and also at the end, it will build your static files and bundle them using Electron Builder. But both of these will use the same Wolfram language backend that is supported by something called LocalDeploy, which is a packlet written specifically for WRB. And as well, their interface with the backend is going to be abstracted away with something called the IPC API. So essentially, what that means for the developer is that they will just develop the front end agnostically of a distribution environment. And then when they go to distribute, they can even do a yarn build desktop or a yarn build web, and that will output the correct kind of build files. So let's start with the Wolfram language side of this. So when I was doing this during development, I thought about a lot of different ways to kind of handle this. This could have been, so we could have just continued to use cloud APIs, right? So I could have easily deployed on the Wolfram cloud any API or any expression, and then done the kind of an HTTP request over the network to that and grab the result back in the application. The reason I didn't go for that is for one, I wanted everything to be processed locally, and two, I wanted to kind of detether myself from the internet. That would require an internet connection with that application, almost defeating the purpose of having a desktop application, right? So what I did instead is I wrote something called LocalDeploy, which is a packlet for, it kind of tries to emulate the behavior of the Wolfram Cloud locally on your machine by deploying expressions on your local host. And it does this by deploying them as TCP sockets that accept HTTP requests. So before we move on a little bit, what do we mean by socket? So a socket is simply a pipe or a memory buffer, which allows two processes to exchange data over a network. So a pipe exchanges data over the same kind of machine, whereas a socket will exchange data over two processes that are separated over a network. And pipes in Mathematica are treated as streams. So that's why you will see them that's where you'll see the Wolfram language function be inside Mathematica. Streams can be pipes, they can be memory buffers, they can be write to these streams. We can read from the streams in the same way, and sockets are also treated in that way, although they are behind this other symbolic object called a socket object. But we use TCP protocol specifically, so we can do HTTP requests, and also it kind of sets up the bidirectional full duplex protocol for us, so we can make a request both ways. Right, so let's start simple and build up our local deploy function by talking about the socket link functions that are built into Mathematica. So there's a bunch of socket link functions that are built into Mathematica, like socket open and socket listen. Socket open can be used to just open a socket on a specific port using a specific protocol. So the protocols that are supported by default are TCP and ZMQ. I went with TCP specifically so we can hit them with HTTP requests. So here we can define our port, define a callback function. We open our server on this specific port. So this will open a socket object here on a local IP address on that port. And then if we want to set up a listener on that socket, all we have to do is put it through socket listen on that server and run whatever data is written to that socket, run it through the callback function that I'm giving you. Right. So if I define this to we'll get out my socket object and my socket listener. And again, the socket listener will be associated with this socket object. And now if I want to connect to it, I don't have to go through an HTTP request. I can actually just kind of directly connect to that socket using socket connect. And that will give a new socket object that corresponds to the client socket. So with this, if I evaluate this, here's a new socket, and now I can treat this as a stream, so I can write to it. So I can write to the client, I can just write the line hello world, and if I did this, this would get echoed out in console, right? So for the server, data has been written on that socket now, and here's the data. We've just echoed it out in full. And you'll see there's a bunch of keys associated with that, like the source socket. So that's the socket that kind of initiated this connection. We've got the data here in a few different ways. So we've got the raw data, we've got the bytes of the data, and the data as a byte array. And all of this stuff is stuff that we can access in our listener function. But what's kind of more useful is if we hit using an HTTP request. So I can just construct the address of that socket by saying, do an HTTP request on localhost at port 12345. So I construct this address, and then I can hit that using URL execute, which I'm not going to do, because if I did, it would just make my kernel hang until I aborted evaluation. And the reason is, go a little bit back, this function doesn't actually ever send a disconnect signal. It echoes the data out, and then the connection just is left active, right? So what we need to do is change our listener function to handle that. I'm just going to write this helper function here just for this talk, just so it's a little bit easier to read. And now we're going to set our listener function to this one. So this is going to do exactly the same thing. We're going to echo our data, but after that, we're also going to close the connection to that source socket, which we're going to call client. So we're going to actually handle we're going to send a close signal. So we can run this through, change our option, and then when I run this, I still get an error, but it will successfully finish, right? The error is just to say, hey, I've not got a response back from the server. This is an HTTP request. I have to get an HTTP response back, but it didn't get anything, so that returns an error. So to handle that, all we need to do is just write some data back to the client. And thankfully, because we're using Mathematica, we don't have to manually write a function to build our HTTP responses. There is one built in. It's called generate HTTP response, and we can export that as a string using export string. So all we've changed here, again, we've defined our client, echoed out our data, and then all we do is write to that client, write a string. We're going to generate an HTTP response of some expression, in this case, just the string hello world, and then export that as a string with the format HTTP response. Right, and then again, close the connection. So now when I make the request to that URL, I actually get some data back. It's a successful request, right? Something else I need to handle is the kind of request parameters, if I need to give parameters in, and thankfully generate HTTP response will handle that too, emulating the behavior of the Wolfram Cloud, so we don't actually have to do much. So here, if I define a dispatcher, which is a way to kind of separate an endpoint into multiple endpoints, so I can have a square endpoint and a cube endpoint that each correspond to a different API. So here, all I need to do is, again, the same thing, with the only difference that I actually import my data in. So whatever the data that the client is sending in, I import that byte array and use that as a request for generate HTTP response. So it's just the second argument of that. And again, now I can hit that URL at the square endpoint or at the cube endpoint and use the corresponding APIs. Finally, just to finish off with this, write string is non-blocking. So if when the kernel gets to this, it starts writing the data to the client, but it will continue with evaluation whether it's finished or not. It doesn't check whether it's finished first. So so instead, in the real local deploy, we use something called socket write message, which is from the 0MQ link experimental packlet. You can import that as well in your Mathematica. But basically, instead of writing strings, we write byte arrays, and it is blocking. So it does make sure that the data is finished writing to that stream before continuing with evaluation. But everything else is exactly the same, right? So we define our client, our request, give it to generate HTTP response, and this time, instead of export as string, we export byte array. Right. Another small thing is we had to handle coarse pre-flight requests. So a lot of browsers will precede a post or GET request with an options request that just asks the server, hey, what are your kind of allowed methods? What are your access controls? And all we need to do to handle this is pretty simple. We'll just, in our listener function, we'll add a condition to check if it's an option request, just return an empty HTTP response with these headers, which can correspond to what our server properties. And then if it's not, just handle the request properly. So let's just show an example. So this local deploy, like I said, is on the packlet repository, and you can kind of install it in by doing packlet install local deploy. We can import it in using, or we can get it using get. And now we can make use of it. Local deploy of an expression. So here I'm using a URL dispatcher. Will return a local deployment object, which is kind of this object representation of that local deployment. It has its socket associated with it, its listener, all its endpoints mapped out, and so on. And again, we can hit those using URL execute and just show that you can do static data, you can do API functions, you can do delayed data as well. So I can do a delayed rule, and this expression will get evaluated every single time I hit this endpoint, and same with this, right? So I can do delayed in a couple of different ways. Cool. So now we've got local deploy. We've got a way of actually deploying Wolfram language expressions on the local host. We need to, one, define them. So what are the expressions I'm actually going to be deploying? And two, write a script nobody's going to be able to then invoke to activate or deploy our Wolfram language expressions. So first thing we're going to do is going to create just an expressions file that's going to have all our definitions. So this is going to be in the form of a list of pairs. And these pairs are simply going to be port number and expression. So I'm going to deploy this expression on this port. I'm going to deploy this expression on that port, and so on. Something I want to note now is expressions tends to always have this diagnostics endpoint on port 8888. That's something I use quite a lot. If you're using this, I'd suggest just leaving that in there. So we can now write our actual deploy script. And for that, we're going to use Wolfram script with the .wls extension, which denotes a Wolfram script. And for those who aren't familiar with the Wolfram script, it's basically a way of writing Wolfram language. I can write a script that when I invoke it in command line, so Wolfram script of that example script, it will just go through line by line, evaluate each line, and then at the end of that script, it will give an exit code 0. Right, so that's straightforward enough. So let's cover a few things that we use for this deploy script. Couple of things. I kind of wanted to have temporary messages echoed out in console during kind of this deployment, but there isn't a built-in Wolfram language function to do this. So I wanted to kind of emulate print temporary, but in command line. So echo temporary CLI was written for this, and this is just a small example of how it works. It simply just writes to the standard out. So it grabs the standard out stream and writes these escape characters to it. So these simply move the cursor back one line and delete that line, and that's it. And as well, we did command line parse. So I want this script to be able to take command line arguments. And so I wrote a function to specifically parse the command line of a script, and that is called command line parse. Cool. So with those, I also want to mention that all of the expressions that we have, so every single different port that we're going to deploy, it's going to be on its own distinct kernel worker. So we're going to do something like this, where each local deployment, where we get our expressions and we deploy them one by one using parallel submit. So this means we are creating a asynchronous task that is submitted to a specific kernel worker, a different kernel worker. And then by wrapping everything in wait all, we're actually making sure that that asynchronous task then evaluates, right? So what that essentially means is that each one of these expressions, so if we go back to this, each one of these expressions gets its own kernel, right? So I can hit URL dispatcher, I can hit a live queue and example, I can hit both of these concurrently, and they can return a result to me without a problem. Cool. And finally, last little thing, there'll be a line in there to block IO, because like we said earlier, once Wolfram script runs all the lines, it just exits the script, right? So we want some way to say, hey, don't actually exit the script, leave this running. And the way I do this is just by having a while loop to check for user input. So at the end of the file, there's just a while loop that checks for user input. And if that user input is exit, it then escapes this while loop, it breaks this while loop, and then it proceeds with evaluation and in the script. And if the input is anything else or nothing, it just perpetually blocks evaluation there. So let's show this deploy script. Let me just open VS Code. Here we go. So here's our final deploy script. We have, instead of importing these helper functions in from the resource center, I've actually exported them. I've done that in a different file. I've imported them in and exported those definitions as WXF using something called dump save, which you can use in Mathematica. And that means I get these WXF files that I can just load in to get the definitions for those functions, and it's a lot quicker than kind of reaching the resource center. Let me zoom in. Actually, someone just said, let me zoom in VS Code a bunch. There we go. Let's do another one just for good measure. Cool. So we load those functions in. We then load our local deploy packlet, and we continue on. So if you notice, echo temporary is used on every step. The way this works is while this is being evaluated, console. Once this is done with evaluation, this then gets deleted from the console. So we load our local deploy packlet, we import in our expressions and just check they're formatted correctly. We launch our parallel kernels, making sure we don't launch more than we need. So I'm only going to launch as many as we have expressions, or with a maximum of however many my processor allows. We're going to pass the command line now again using command line pass. We're going to grab the base. So by default, we leave it as localhost, but obviously we can change that. Sometimes our base might be different, so we can give that in as a command line argument. Distribute the definitions. So we distribute the definitions to the parallel kernels because they don't by default get those definitions. And finally, this is the actual deployment step. I want to ignore this whole thing because this whole thing basically is just printing. This just generates messages for printing. The actual content of the thing is basically just this, right? So we map apply our expressions onto this. We take the expression, give it to local deploy, take the port, give it to local deploy, and deploy that using our kind of parallel submit wait all method. And finally, just some error logging here if we need, and our while loop just to kind of prevent the script from ending. Okay, I hope VS Code, I hope the zoom in of VS Code is a little bit more readable. Some people say that it's not very easy to read, which I don't disagree with. But with that being said, that's a deploy script. All it does is it loads our expressions, deploys them using local deploy, and just stays active until we say otherwise. So I can show what that looks like. Yarn start WL to just show what that would look like. So there's our temporary things being printed out in console. So we know what it's doing. And finally, it's going to give us a nice message of what it's done. So it's done 2 deployments, one on 4848, one on 888. And here's the endpoints on each of those deployments. And finally, it blocks this script from ending. If I enter anything, it won't. And I can either give it an interrupt signal or just an exit input, and it will end that script. Cool. So let's go back to the notebook. There we go. And continue on with how we're going to manage this as a process now, right? So we've got a deploy script that when we run it, it deploys our local deploy scripts and stays active until we tell it otherwise. So let's now kind of manage this through Node. And the way we're going to do that, there is a module called child process that kind of manages this. It has a method called spawn that I can give it a command, some arguments, and that will go off. It will spawn that as a subcommand of our Node process, and then associate a process object with this variable. So then I can do various things, like I can set up event listeners. So just to say, here we're running our Wolfram script, just some initialization flags, and then finally we give our script here by doing require.resolve of our Wolfram language package, right? So our Wolfram language package, that's its main kind of export, is that Wolfram language script. So by doing require resolve of that, it gives us the directory for that script, right? So now what we can do with our process object, we can set event listeners on various memory streams. So standard out, I can set up a listener on that. So when data is written on standard out, convey it to a string and log it to console, or on standard error, do the same. I can do the same for exit. So if that process exits, console log out the exit code and show an error box and start the process again, right? So that WL-proc is used to then manage the lifecycle and also listen in on what's going on to that process, with that process rather. And finally, just something to mention, something else that needs to happen. Obviously, these things need to let the front end know that, hey, the Wolfram language is either ready or it crashed and you can't make requests to it. And the way it does this is with something that we've touched on, not got to yet, but this IPC mechanism. So it has to send a message to the front end and say, okay, the Wolfram language status now is 0, right? So we're good, you can make requests. Whereas if anything bad happens, it sends a different status code and that gets interpreted as bad. And then the front end handles that however it will handle that. Right. So in the front end, all we're going to do is API, IPC, listen into this Wolfram language status channel, and then do what we will with the received code. So if it's 0, we're all good. If it's not, then we're not. Cool. So now let's actually touch on the IPC API. Right. So the whole idea of this was that this project started out as simply Electron. It started out as a kind of Wolfram language and Electron framework where you could do this local deploy stuff to build your own standalone desktop applications. And that was great and all, but the moment I started trying to extend it to also cover the web, I realized that there was an issue with any implementation that used Electron's IPC. Well, Electron's IPC is a purely Electron thing. So anything that I do through that mechanism, I won't work in the web. Right. So the moment I go to deploy in the web, that falls apart, that doesn't work, that needs re-implementation. And then I've got the problem that I had before, which is 2 different front ends for 2 different deployments. So what the IPC API does is, since we are defining our front end as just a standalone React component, that then is able to take an API as a parameter. Right. So in the case of Electron, for example, we can pass in our Electron IPC and pass that in to our front end when we are actually creating our desktop index for that application. And as long as that API follows this interface, then we're good. So it just needs to be an object that has an environment key that corresponds to one of the allowed environments. IPC object that contains these methods that abide by those type definitions. So as long as our API abides by that, we don't care what methods it actually uses behind the scenes to kind of make that happen, right? So let's talk about the specific implementations of this. So in Electron, like we've been saying, we use the Electron IPC. So both the use Wolfram language and use IPC go, both of the hooks go through the IPC API, which use Electron's IPC to then communicate with that main process and the Wolfram language process, right? All the API stuff is exposed through the window object. So again, let's go back to VS Code. So if I show our preload script for Electron, here's where we actually define that Electron handler. So you can see here's our environment key, here's our IPC key, and we're just exposing a bunch of IPC renderer methods, right? So send goes to send, on goes to on, that handles the kind of dissolution of that listener. Once goes to once, right? So pretty straightforward. And then this is the kind of pure Electron thing. In Electron, usually what you would do is you would have this context bridge exposed in main world where we are creating this API object in our window object. So the window object is an object within JavaScript. Then when you are in the render process, you can at any point do window.api.IPC.on, right? So you can have access to these methods. Obviously, that would only work in the case of Electron. So what we do instead is when we go to kind of define our index, we bring in our front end here. We bring in our front end and we just give that window object in that API that we've defined. We just pass it into the front end that then does with it what it wills. Cool. So all our Wolfram language handling as well, that happens in the main process. And we'll kind of show a few functions of that later, but essentially what it is, there's kind of the same functions for both Electron and desktop, and these correspond to kind of these. So there's a check Wolfram language function, there's a start Wolfram language, a cleaner Wolfram language, and a request. Right, so those are the 4 main functions, and in the case of web, we'll have an alive queue as well. But the idea is that I can, that these are all the functions I need to manage that process, right? And then we set up some event listeners here to actually manage this. So we set up an event listener on the start Wolfram language channel. So if we get any message on the start Wolfram language, we start Wolfram Language. We set up a request channel, so the backend needs to make the request, because obviously the request method will differ between Electron, Web, or any other deployments. So we set up this request event listener. So on the request channel, we're going to take in some arguments, give it to our own backend request function, and then this request function is going to write back to that. So it's going to actually send back a reply to that. It's going to send back a reply to that event from the renderer. Finally, this is a non-Wolfram language thing. This is just something I added. Control zoom doesn't work on Electron by default, so there's just an event listener for that. And finally, we clean up we just check at the end. So if we're going to close the application, we clean up the Wolfram language before that. So we just close the process and get rid of it. Cool. So let's talk a little bit about the front end side. So in the front end, like we said, all we do is just pass the API to the component, and then finally, after all our other listeners, we send the message to the backend to say, hey, start the Wolfram language with an empty array. Obviously, it doesn't take arguments, because it just, as soon as it receives the message, it just goes off and runs the start WL function. Cool. So the web IPC now tries to kind of emulate this. It tries to work in the same way, but instead of using Electron IPC, it uses something called socket IO. So it connects two sockets, a client socket and a server socket, using this socket IO stuff, and then that allows us to set up the same event-based communication between backend and front end. Right, and this is done through, is exposed through something called the web handler. So instead of having our Electron preload kind of window object, we actually define a web handler class. So let's show that now. So that's in our web package. Here's our web handler. And again, it is very similar to the other one. It almost does exactly the same thing. Here it sets up our on, send, and once, which just expose different methods of this socket. The only difference being that emit had to be used for socket, because emit is closer to what Electron send does. But essentially, it's the same exact thing as the Electron one, but this is a class instead, just because it uses a constructor to kind of distribute this socket around and have that be available for each one of the methods. All right, and the other thing is our Wolfram language is also managed by a distinct class called the Wolfram Language Manager class. And that is, again, for the same reason, because this will take in, let me just collapse some of these sections down, because this will take in as input a socket and a client socket and a server socket, and we'll kind of distribute that around to do checks like, you know, if, where is this? So if there's more than one person connected to this server, don't close there, don't clean up, right? So I need to check that, you know, there's 0 users connected before I actually go through and clean up that process. Things like that. But essentially, it is the same thing. They both use no child module. They both just use spawn. So if I show start WL, it's essentially the same thing here, where it's just this Wolfram language command, which changes depending on platform. So Wolfram language command, same kind of arguments, and then our script. Cool. Let's go back here and just talk about the IPC server now. So we've talked about kind of all this side of the stuff, but we've not touched on this IPC server that we're reaching now, right? So this socket, this client socket needs to have some server socket to connect to, and that is where our WRB IPC server comes in, which kind of emulates the main process in Electron. That the WRB IPC server is your main process if we're talking about this in a renderer main process kind of thing. So all this is it sets up an express HTTP server, right? So it accepts GET and POST requests from anywhere. You can actually restrict this down to specific origins, but I did not. And then we just, same way, set up a listener inside that node file to check for connection. So if we get a connection from a client, we just log some stuff out, and we start a new Wolfram Language Manager using that socket. So every single client gets their own Wolfram Language Manager. We then start the Wolfram language. So if you remember, this will only kind of do anything if there's not a process already started. Set up the request listener for that client. So if they send a request through, it will get through on here, and we will use the WL manager request method to do the same thing, send the data back. And finally, on disconnect, we just, again, log some stuff out. And if there is 0 users left, we clean up. So again, we leave this process running for a while, right? So there is actually a countdown, a timeout, sorry, on cleanup WL. So when the last user disconnects, it gives it like 5 minutes and then closes down that process. If another user connects in those 5 minutes, then it just stops that timeout and, instantly loads the page. Cool. So finally, with all that out of the way, let's show just the example of the front end. And in the front end of the web, all we do the same thing, but instead of giving a window.api, we just create our web handler from our socket. So again, we're using socket.io to create a socket. This stuff, just ignore for now. That's because this is meant for deployment on the Wolfram application server. And so by default, the server runs on port 3000. However, on the application server that runs inside a Docker container, you have to expose a specific endpoint through Nginx. So I exposed this kind of /.ipc, this .ipc endpoint that corresponds to port 3000 of that container. Right, so I'm just saying, if I'm in production, I should hit my the actual .ipc endpoint. Cool. But all we do, send our API to our front end and just set up the listener. So on connection, we send the start WL signal, and on disconnect, we disconnect that socket from the server. Right. And now with both of these, with both web and Electron, what that kind of achieves is this use IPC hook. So me as the developer, all I have to do as a front-end developer is just call on this use IPC hook, and I don't care what environment I'm in. So what does this look like? So here I've got a component that is within an IPC provider. This stuff is pre-set up for you. So if I go to the actual project front end and look at the app, so you'll see the IPC provider and Wolfram language provider, which we'll get to, are both set up for you, so you don't have to do this. Right, so that kind of passes down the context of those functions and the although those methods, passes them down as a context to all its kind of children components, all the React components that are within that IPC provider. So within that component, say I wanted to use the IPC, all I do is I can deconstruct it into different parts. So I can grab the environment or the IPC and then say, just use those methods. So IPC.once, set up a one-time event listener, send a message, send a message to the backend, or set up a persistent event listener, right? But this is done the same whether I'm using Electron, whether I'm using the web, or something else, right? So the front-end developer always just calls on IPC once and expects that API to always have that method available and to basically do the same thing. Cool. So with that being said, let's talk about the use WL hook. So this is kind of an equivalent to use IPC, but instead of the IPC, it allows you to interface with the Wolfram language instance. And it also uses the that use IPC hook to make those requests, because obviously they differ between environment. But essentially what this hook does, it gives you two things. It gives you the ability to make the requests, and it gives you a kind of variable where you can check the status of the status of the process, right? So the first thing we do is we set up an event listener on our Wolfram language status that checks for any codes that are not 0. We handle that code. We set is active to true if that code is 0. We set it's false if it's anything else. And we also set up a listener here. We set up an interval 15 seconds, hit our diagnostic endpoint. So that live view endpoint that we're just talking about, that just returns true if it exists and is active. So we just hit that endpoint every 15 seconds. And if that returns false, then is active is set to false. Whereas if it returns true, then is active is true. So again, we check every 15 seconds that our Wolfram language process is reachable and active, right? Requests, this is how they're handled. So since the backend has to handle it, all the Wolfram language hook request function does is actually send. It uses the IPC API to send a request to the backend and then sets up a one-time event listener to receive the reply from there. And finally, as the bit that's actually important, how you would use it as a developer is, I've got here, again, your Wolfram language provider is set up. I've got my component that needs to make use of Wolfram language. I deconstruct it into parts. So I've got my request here. I've got is active, and I can check. So if is active, render this component, and then my button on click runs a request from use.wl on this endpoint with this parameter value on this port, right? But remember, this is not going to make the request on that port. This is going to send that request to the backend, which is then going to make that request to the Wolfram language. Cool. So last little few things is to talk a little bit about yarn, and then I just want to kind of just show the boilerplate working. So by default, most React projects will use kind of NPM by default. So NPM is Node Package Manager. Yarn is an alternative to this, is another package manager, with its strength being it kind of being more deterministic in its log file, which is how it logs your dependencies, and also just being slightly faster in building, right? But also the main reason why we chose Yarn, like I said at the beginning, it allows us to use that Yarn workspaces feature to manage our multiple sub packages, right? So here's all the different sub packages that are part of the boilerplate. So we've got our front end, which is our React component, Wolfram language containing all our Wolfram language scripts and files, our Electron package, which is our desktop distribution, and finally our web package, which is for web building. And there's a bunch of scripts that are available on the kind of root project that I can use to then either start a dev server, package my app, build my files, or what have you, right? And how I do that is I would just, in the root of the project, I would just do yarn, say package Linux, and that would go into my Electron project and package a Linux installer for that. So before I move on, just about the scripts, all of these are defined in package.json for the root project, but there is also kind of subscripts for each project, right? So for each sub-project, they get their own package.json with their own scripts. And we can also call these from root if we just do yarn, workspace, sub-package name, command name, right? So that is how we interface with the scripts. But right, with all that out of the way, I just want to kind of demo the thing a little bit. So let me exit full screen, go into VS Code, and let us just close everything. Cool. So now as a developer, let's clear this as well. As a developer, I come in, I go into my packages. This is where my sub packages live. I say open my front-end package, and in the case of the demo, I can go into my demo component, which is the main kind of component that we're rendering. And here's all the definition of that. If I want to kind of, get a dev server running for my Electron version, I can just do yarn dev Electron, right? So that will go away to the Electron workspace and run the dev. It will run the dev script. So there we go. We got our Vite dev server, and that opens on another window. Let me drag that in. That starts our application, and you see that now starts our Wolfram language instance. And once that's ready, we'll send the kind of ready signal to the application. There we go. Loading's done. Our local deploy functions are ready, and now we can use this as any other application. So I can test their input. So I can say if by the way, this is just for testing. If this would be an actual nightmare if this was your application and you just have Wolfram language input, because you would, it would be a security nightmare. But all to say, this is just for demo reasons. So we can do 2 + 2, for example, something really simple, and see that show up in our backend. So here it is. It comes in as an evaluate request with our parameter in 2 + 2, and that result I get sent back. And I can do other things. So the first request usually is somewhat slow, and then the concurrent requests are reasonably snappy. right? We can see all that logged out in our console. So I did that just for debugging. It just helps with that. And for this demo, you can also use external evaluators from Mathematica. I've not got them set up on this machine, so I won't do that. But again, I just close this out. Oh, actually, before I close this out, I also want to show that hot reloading works. So if I am actually actively developing here, right? So let's put this to the side. If I'm actively developing, I'm in my front end. The way this gets imported, it can change anything in this demo. So what's this? So let's change this wording, computational intelligence. Let's just delete that. And if I save that, that will get reflected in my application, right? Without me having to recompile everything. And the same goes for the web application and also the node server. Everything has been set up with hot reloading to any changes that you make, you just do Control S and that reloads your dev server. Right, so let's close that and now show the dev version. So we can do yarn dev web. Right, so you can see this is actually running two processes concurrently. It's running our dev server, so that's our node server, and it's also running our client, which is our Vite dev server. So this I have to go to manually. So let me localhost 5173. That will open the same application. Again, we see that coming in our console. I've got a connected user. We've got our Wolfram Language PID, and it's going through the kind of startup procedure right now. There we go. It's send the signal back to our web page, and now I can again use it as before. It will send that request to the backend, and now I can just do whatever I want. I can open more instances just to show how that works. So, if more users connect, we're not going to start another Wolfram language process. There is only one Wolfram language process on the server, right? So all of these will use the same one. However, once I close a couple, so closing these two does nothing, right? But when I close the last user, it will say, it will schedule the termination for the process. In dev mode, it will be about a quarter of a minute. In production, it'll be about 5 minutes. And then after that timeout is done, it will just end that process and just kill that, right? So there it goes. So it's still active. I can still open that web page, and if I open it, it will again start a Wolfram language process and go off and do its thing. I'm just going to do Control-C to kind of stop those servers from running. And finally, I just want to show if you want to package your application for desktop now, I just want to do yarn package Linux, right? All right, actually, we'll do Windows, sorry, there we go. Package Windows, and that'll go off and again run that script, compile my TypeScript and React into static files, and then use those to build a installer file. And all of that stuff would go. Let's make that full screen again. All that stuff goes in here. So in your Electron package, inside out, there is a build folder with all your kind of files that you've generated. So in this case, I'm generating a exe installer. I can also generate app images. I can generate kind of Debian installers. All of that stuff is set within the package build option. So you can see here, there is some build options. So this is where I'd set my project name, its version, what the app ID is. And also here, I can set different stuff about different metadata about the installers that I'm producing. So for example, for Windows, I'm targeting NSYS. For Linux, I'm targeting an app image, but I can add a Debian in there, a kind of .deb installer as well if I want. Right. So with that out of the way, that's kind of it for main content. Let me go back to the presentation just to say there's a few other things that I've not touched on. So this boilerplate adds a bunch of other stuff, right? It allows you to play with. So Jest is built in. That's for front-end unit testing. So I can do things like, see that? So I can do yarn test, and that will run some front-end tests that are stored within here. At the moment, they're just basically placeholders. It is just checking that the front-end renders, and that's it. And again, this is treated as a separate environment with its own mock APIs and files and stuff. So here's the mock kind of IPC API for Jest, which literally does nothing. But yeah, that's preset up for you. We've got GitHub Actions as well, they're preset up as well. Like we've got this test workflow preset up that will just run through the jest tests, and it will also just try and build both Electron and web just to make sure that no errors are returned. And this will happen every time you push or do a pull request on any branch. But obviously, you can change this as you please. And there's a bunch of other stuff like editor configs. I've got Prettier and ESLint set up for linting. There's a lot of things set up. The TS config is kind of a long thing. But yeah, everything's kind of been pre-set up for you. So you go to the repository, and I'll show that now. You go to the repository, and there will be a use as template button at the top. So use this as template, and then you can just create a new repository with this as a template, and you can just go in and edit the parts that you need to edit, right? Which specifically would basically just be the front end, right? If you wanted to do something like this and you didn't really want to change much of the backend, what you need to do is go into the front end, change your components, change this front end layout, and then add any backend functionality you need if you need it extra, right? Add your expressions to the Wolfram language. Where is that? So add our expressions to WL. If I want to deploy something else, again, I just add it here as an expression port pair, and that's it. Cool. So with that out of the way, if there's any questions, I'll stick around for about 5 minutes. But if not, I appreciate you listening. I hope this has been informative and enjoyable. And thank you all for listening. I forgot about the Q&A section. Let me just answer this stuff. Can we share a notebook presentation? Actually, I think I might upload this on, so I've got a commit this on here. I think this is going to be part of the GitHub. So I think if you go into that GitHub in about probably an hour's time, this notebook and another notebook that's a more article type, that will be there in the docs folder for you. Can you, so for examples for this project, I am actually currently using this for something, but because they're internal consulting projects, I don't think I can talk about them too much. But all to say that, yeah, I am actively using this on a customer project right now. So that it was written with that in mind. Source code files, yeah, source code files, all of that stuff is on the GitHub page. I'll actually put that on screen as well, including some probably subpar documentation, but it's there. So yeah, all of this stuff is, I try to document on the GitHub page, including all the stuff about the was. Cool. I'll close out there. So again, thank you everyone for listening, and I hope you find it interesting. Bye everyone.